Have you ever wondered how scientists study the geology of other planets? It's a question that opens the door to a world of exploration and discovery. Planetary geology, or astrogeology, is a fascinating field which involves studying the solid bodies of our solar system, from planets like Mars and Venus to moons, asteroids, and comets. Why is this important, you might ask? Well, by understanding the geology of other planets, we can gain invaluable insights into our own planet's history and future. We can learn why Earth is habitable and others are not, or how geological processes on other planets compare to those on Earth. We can even seek answers to the age-old question of whether there's life beyond Earth. From the rocky red surface of Mars to the icy moons of Jupiter, every mission and every rock studied takes us one step closer to these answers. Today, we'll dive into the fascinating process of studying planetary geology. The journey of studying another planet's geology begins long before we ever set foot or rovers on its surface. Indeed, the first step to studying a planet's geology is the meticulous planning phase. This is where the groundwork is laid for every successful space mission. So, how does it all begin? Well, the first thing scientists do is choose the planet they want to study. This decision is based on a variety of factors, including the planet's proximity to Earth, its atmospheric conditions, and the scientific questions they hope to answer. For instance, Mars has always been a favorite choice because of its similarities to Earth and the potential for discovering signs of past life. Once the planet is selected, extensive research is conducted about its environment and conditions. Scientists delve into the planet's atmosphere, gravitational pull, temperature, and more. They utilize data from previous missions and telescopes to understand the planet's terrain and weather patterns. This research is crucial because it helps in designing the spacecraft and the instruments that will be used in the mission. Designing and building the spacecraft is a complex process that requires a blend of engineering and scientific expertise. The spacecraft needs to be robust enough to withstand the journey through space and the conditions on the planet. It has to be equipped with the right instruments to carry out the planned experiments. These instruments might include cameras for capturing images, spectrometers for analyzing the composition of rocks and soil, and drills for collecting samples. Building the spacecraft is a collaborative effort involving hundreds of scientists, engineers, and technicians. It's a process that often takes several years, with each component meticulously tested to ensure it can withstand the harsh conditions of space and the planet's surface. The planning phase is not just about designing and building the spacecraft, it's also about planning the mission's objectives, the tasks the spacecraft will perform, and the experiments it will carry out. Once the planning is complete, it's time to launch the mission. The spacecraft, with its precious cargo of scientific instruments, is ready to embark on its journey, taking us one step closer to unraveling the mysteries of our universe. After months or even years of travel, the spacecraft must face the critical moment of landing. This moment, often referred to as the 7 minutes of terror, condenses years of work, planning, and anticipation into a nail-biting span of time. Landing on another planet is no easy feat. It's a carefully orchestrated ballet of technology and physics. The spacecraft, speeding at thousands of miles per hour, must slow down in time to gently touch down on the surface. Imagine you're trying to throw a dart at a dartboard, but the dartboard is millions of miles away, and you're throwing from a moving car. That's the level of precision required for a successful landing on another planet. Let's take the example of Mars rovers. These rovers, like Curiosity and Perseverance, have to go through a complex landing process, aptly named the sky crane maneuver. After entering the Martian atmosphere, a parachute deploys to slow the descent, but Mars's thin atmosphere can't slow the rover enough for a safe landing, so the rover is gently lowered to the ground on cables from a rocket-powered descent stage. Only after the rover's wheels touch the ground does the descent stage fly away to a safe distance. This entire process requires precise calculations and advanced technology. The landing site must be carefully chosen to ensure the rover's safety and to maximize the scientific value of the mission. But even the most meticulous planning can't account for everything. Mars' unpredictable weather and rough terrain present additional challenges. The landing phase is a critical junction where years of planning meet the harsh realities of space exploration. A single miscalculation, a tiny glitch, can jeopardize the entire mission. but when it all goes according to plan, the reward is immense. A new world ready for exploration, holding secrets about our universe and perhaps even the origins of life itself. Once the spacecraft has safely landed, it's time to start the real work. The rovers, now on Martian soil, are ready to begin their mission, to study the red planet's geology and search for signs of past life. Now that the spacecraft has landed, it's time to start collecting and analyzing data. A variety of tools are used to gather data from these distant celestial bodies. Let's take a closer look at some of these mechanisms. Rovers, for instance, are mobile robotic explorers that traverse the planet's terrain, scanning and collecting data. They are equipped with drills to extract samples from the planet's crust and cameras to capture high-resolution images. In contrast, landers, which are stationary spacecraft, perform on-the-spot analysis. They can drill deeper into the planet's crust, allowing us to peek into the geological history hidden beneath the surface. Orbiters, on the other hand, circle the planet, capturing comprehensive data about its atmosphere, surface, and even its magnetic field. They provide a bird's-eye view of the planet, helping us understand its global characteristics. Once the data is collected, it's time for transmission back to Earth. This is achieved through the Deep Space Network, a worldwide system of antennas that communicate with these distant explorers. The data is sent in the form of radio waves, journeying millions of miles across space to reach us. Upon reaching Earth, the data enters the realm of scientists who are eagerly waiting to decode it. The process of analyzing this data is complex and time-consuming. It involves comparing the new data with existing models and theories, looking for similarities and differences. Each piece of data is like a puzzle piece, helping to build a clearer picture of the planet's geology. This data analysis is not a one-time event. As new data comes in, the understanding of the planet evolves. This continuous learning process allows scientists to refine their theories and make new discoveries, pushing the boundaries of our knowledge about these distant worlds. The data collected provides invaluable insights into the geology of the planet. It's like piecing together a cosmic jigsaw puzzle, each data point adding a new piece to the picture, revealing the secrets that these alien landscapes hold. It's a fascinating process that gives us a glimpse into the mysteries of our universe, one data point at a time. So, what have we learned from studying the geology of other planets? Well, it's as if we've been handed a cosmic magnifying glass, allowing us to peer into the past of our own planet and the potential futures of others. One of the most riveting discoveries has been the evidence of water on Mars. It's like finding a needle in a celestial haystack. Traces of minerals like hematite that form in water and the presence of ancient riverbeds and deltas tell us that Mars was once a warm and wet planet, possibly hospitable to life as we know it. But the story doesn't end there. We've also found evidence of ice at the Martian poles and below its surface, suggesting that water, a key ingredient for life, is still present. This is not just a big deal for Mars, but it's a giant leap for our understanding of where life could exist beyond Earth. Now, let's hop over to Jupiter's moon, Io. This celestial body is the most volcanically active place in the solar system, a real-life inferno in the icy void of space. The constant volcanic activity, observed through missions like Voyager and Galileo, has shown us that Moon isn't just a passive chunk of rock orbiting a planet, but a dynamic world with its own geological story. Io's volcanoes are so powerful that they spew out plumes of sulfur and other materials up to 250 miles high, which is almost unimaginable. This volcanic activity is driven by the gravitational pull of Jupiter, leading to a process called tidal heating. It's like Io is caught in a cosmic tug-of-war, and the result is a spectacular display of celestial fireworks. These insights not only help us understand other planets, but also provide valuable lessons about our own planet. Studying the geological activity on Mars and Io allows us to draw parallels with Earth's own geological past and present. It gives us a unique perspective on our place in the cosmos and underscores the importance of continuing to explore and study the universe around us. So there you have it. That's how scientists study the geology of other planets. We've journeyed together from the meticulous planning phase, where mission objectives are set and technology is fine-tuned, to the daring journey and landing, where spacecrafts navigate the harsh conditions of space to touch down on alien worlds. We've explored how rovers and probes collect valuable data, employing a host of sophisticated instruments, from lasers and drills to spectrometers and cameras, to analyze the composition, structure, and history of these distant landscapes. And we've seen the incredible insights that have been gained, from the existence of water on Mars to the active volcanoes on Jupiter's moon Io and the icy geysers of Saturn's moon Enceladus. The exploration of other planets is a testament to human curiosity and ingenuity. The next time you look up at the night sky, remember the incredible work being done to unravel the mysteries of our universe.